Okay, I think we'll try to get started again here. Our next speaker is our own Marty Bollinger, and I won't say too much because he uploaded 140 slides for his 45-minute talk. But I will say that, on Saturday, if you came here from somewhere else, you're going to go home and the workshop will be over. But for the faculty and students here, many aspects of what you guys are all doing this week are ongoing. So for us, the workshop never stops, in a sense. And that's a direct consequence of the efforts of Marty to build a highly complementary and collaborative group of researchers here that has enabled everything that you guys have experienced this week. So he did that, I think, out of a vision and a belief in a concept that's really important to any scientific endeavor, and that's that you can do more as a team than you ever could as an individual, that the whole is more than the sum of its parts. So we're also very lucky to have him here speaking about tools that you can use to elucidate mechanism in metalloenzymes. Please join me in welcoming Marty.
Thanks, Amy. It's a pleasure to have a chance to talk about some kinetics topics. So as a kineticist, I thought that I might try to encapsulate the workshop from my perspective by some kinetic measurement. So I came up with something that kind of resembles what you do in single molecule kinetics, where you make a number of observations and then you bin them, and you create a set of kinetic data that way by individual observations. And so the one I came up with is shown on this plot. And what it is, it's the incidence of emails emanating from Karsten Krebs' account to my account, binned on a per-month basis, okay? And so you can see that there's some real nice kinetic data in this plot, and as any good kineticist would do, when I see data like this, I have to fit it. And so here's the fit that I think best describes it. And what it is, it's actually, we use the program Kaleidograph to do a lot of fitting, and it's one of the built-in equations. It's an exponential growth, and it's sort of what you would see if you grew a bacteria culture, because each bacterium that reproduces can make another bacterium, and so they multiply rapidly. And you can see it fits pretty well to the data. And if you allow me to change the scale, both the limits and go from a linear to a log scale, I think you'll see why I'm personally very happy that the workshop was scheduled in June over the summer break and not in December over the winter break. As you can see, the y-axis here would be pretty daunting and might crash my computer. Okay, so this is by way of thanking Karsten for his heroic efforts every 2 years in organizing this brilliant event. It enriches us in our research program, personally in meeting all of you. It's something that I never could have anticipated when I came to Penn State as essentially the only bioinorganic chemist in 1995. And it's a realization of a vision, as Amy said, of a team of people who work together, share credit, and have a lot of fun in the process. So I've also noticed, though, that the workshop seems to be trending toward the structural. There are some exceptions, but the majority talks to me seem to be addressing issues of electronic and geometric structure by, like the talk we just saw by Oliver, X-ray crystallography and spectroscopic methods. And I don't like this. The reason is, the way my mind works, when I encounter something new, and I'm going to tell you about intermediates that are new that we encounter, when I ask, what is it? I don't first ask, what does it look like? I always ask, what does it do? And that's what I'm going to try to tell you about, how you go into an unknown reaction and you try to figure out what each state is. Now, I'm not talking about electronic states, but more kinetic states. and what the components of that state do, in particular the elementary reactions within a reaction cycle. And so what I'm going to present for the next 2 hours, as Amy said, is, no, I'll try not to keep you from your lunch, it's really just three things. The goals and challenges of looking at a metalloenzyme reaction and trying to understand how does it happen, how does it come about. And then I'll tell you about the techniques, and because we cover these so well in the practical sections, I'm just going to very briefly gloss over these and just tell you about the concepts. And what I really want to try to do is present a few selected examples of situations that we've encountered through which we've developed intuition. This intuition becomes incredibly powerful. Because when you start on a new reaction and you start mixing things, you're really very blind, and you get data that's very, very sparse. And to go from that to real insight about how the enzyme works, what are the steps in the reaction, and how does the structure specify those steps to do structure-function relationships meaningfully, it's really pretty hard. And so I hope to impart a little bit of what we've learned from our experience. And I just want to note that I uploaded to the Dropbox in a new folder called Bollinger Transient State Dissection a number of references. One is just this presentation or a slightly earlier version of it, this file here, and then two references that I'll tell you about right now. So in 2006, Karsten and I wrote a review article where we sort of tried to summarize on sort of a methodological orientation of work we had done to that point. That was only 4 years into this partnership that's now lasted 14 years. And so what we called it was stalking intermediates in oxygen activation by iron enzymes. And what it espouses is that when you want to look at a catalytic cycle, an enzyme, it starts off as a black box, and you got to go in and look at the individual states, the individual steps in that reaction, and look directly at them. Okay? And in this review article, what we noted is that we drew heavily from an earlier review by Ken Johnson, published in 1992 in Enzymes 3rd edition, where he covered more generally how you dissect an enzyme reaction pathway by transient state kinetic methods. And Ken isn't particularly interested in metalloenzymes or metals at all, so this is general to enzymology, but it is really a brilliant reference. It contains all kinds of little kinetic scenarios that basically it's incredibly comprehensive. And so that's one of the two reviews, along with this stalking review that Karsten and I wrote. And Ken actually was at Penn State for a lot of his career. In fact, he was the chair of the search committee that hired me here in 1995. And a few years later, he moved on to UT Austin. But he was sort of my mentor for the first 4 years, and I've really become a disciple of the way he's tried to push the field of enzymology, mechanistic enzymology, away from the shackles of steady-state kinetics that the field grew up with before the day that you could make gram quantities of protein and think of them as reagents. But we're beyond that era, and Ken has pushed the field to realize that looking at an enzyme as a black box and looking at the rates of input and output of substrates and products is very, very limited in what you can learn. So you got to go in and look at enzymes as chemical reagents and study reactions in single turnovers, and that's what we're talking about doing. So he espoused this for the field, that direct measurements of reactions at the enzyme active site are required in order to establish the kinetic and thermodynamic bases for enzyme specificity. And so that's really what we're trying to do for metalloenzymes. But there are some unique challenges and really some unique aspects to the pursuit when it comes to the really reactive states that can be generated in the active sites of metalloenzymes. In particular, Carson and I are interested in oxygen activation and carbon-hydrogen bond cleavage, and we get a lot of really reactive states here. Okay, so the goals are we want to detect and get structural information on each intermediate in a catalytic sequence. We want to understand the transition between those intermediates. We want to delineate barrier heights and identify rate-determining steps. That's what any enzymologist wants to do. And then understand how the enzyme, which is a catalyst, it's accelerating the reaction. It's not making something happen that can't otherwise happen, but it's accelerating its approach to equilibrium, how it can lower barriers for individual steps in the reaction, and in particular, understand why it looks the way it does, how that makes it work. And then I think a really underappreciated goal, which underlies everything that we do, is to understand how the enzyme selects against or suppresses other pathways that can occur in the same chemical framework, okay? And so there are some technical and really fundamental obstacles to this pursuit. A technical aspect is the fleeting nature of the intermediate states that we're looking at. This is a little bit old now, and I said at that time that in the best cases we have intermediates that live for microseconds to seconds. Fortunately, enzymes, many enzymes, and especially metalloenzymes, the time scale is milliseconds to seconds, and that's readily accessible by transient state kinetic methods. So, but everything we do is going to involve very rapid mixing, rapid observations, okay? It turns out that this is really not true anymore. After formulating this technical limitation, the next 5 intermediates that we worked on had lifetimes of many minutes. And I don't know why it happened that way, but we just got lucky and started to find intermediates that were extraordinarily and unexpectedly stable. So sometimes you get lucky, but usually you don't. The second barrier is more important. It's very fundamental, and that has to do with when you're trying to go in and look at a mechanism which on paper might have 8 states. It's very likely that most of those states won't accumulate because of the problem of kinetic masking. And that's where if a state is formed slowly and then decays rapidly, it just never builds up. It's impossible to look directly at it unless you can trick that state into accumulating, and that's one of the things we try to do. That was the reason for the stalking term, which actually hasn't worked out too well. I think that was maybe an unfortunate choice of words. So to illustrate this point, I turned to an enzyme, isopenicillin N synthase, and Carson and I formulated the idea to work on this probably around 2006, and we just published our first paper thanks to Esta Tamanaha and Bo Zhang here, who's here at the workshop. In Jack's, it's out online now. And from classic experiments by Jack Baldwin, Peter Roach, and others, this mechanism has been formulated. And you can see there are 3 states on top, 3 on bottom, and 2 on the side, so 8 states total. And when we went in and looked to try to trap intermediate states, we could see, I think amazingly, both carbon-hydrogen cleaving intermediates, this ferric superoxide complex, and later in the sequence, an iron 4 oxo complex. And that was really exciting, but we could only see those 2 intermediate states, and then we could see this boring resting enzyme that you isolate, and then with the substrate bound, we can form all those states and we can see them. And so we take that 8-state sequence and it collapses in a kinetic model into a 5-state model. Okay, so you got to understand this idea of the kinetic collapse of what you would draw on paper to rationalize the chemistry into what you can actually look at and see when you do experiments in vitro. Okay, so that's an important concept. And what it means is, as you get into this sequence, you can isolate these steps just by leaving out, obviously if you don't have the substrate, you'll have this. If you add ACV to the substrate but don't add oxygen, you stop here. So you can kind of look at those independently, but once you mix with oxygen, everything's in there. This state forms slowly and presumably goes rapidly to the next state to the iron 4 intermediate, which we can see. Hydrogen abstraction is slow, but then the recombination that you see to form that 5-membered thiazolidine ring is fast. and so we don't see that state. So we're missing things that we'd really like to look at. And so what we do then is in terms of a general approach, we'll use stop flow absorption measurements to count the accumulating states. And that you can do it a number of ways. There's intuition, there's mathematical techniques like singular value decomposition, and then there's analysis of kinetic traces, and they can all tell you directly or indirectly how many states you need to account for the data you're looking at in a stop flow experiment. We then use two stop time. This is a continuous experiment where you mix it and then you watch it in time. And we use two stop time experiments, a freeze-quench experiment that allows us to focus in on times when we know there are new states formed and find out what they are by spectroscopy. And of course, we're demonstrating both these methods. A method we won't really show at this workshop is chemical quench flow. It's just like the freeze-quench experiment, except you start a reaction, instead of freezing it to non-destructively capture whatever's there, you blast it with acid, base, or organic solvent. The enzyme falls apart. The substrate, whatever state it's in, may also decompose, but you can look and find what it is and infer back to what it was when you killed the enzyme with the acid or base. So this is a really important complement, because while most of our bioinorganic-oriented spectroscopies will focus on the cofactor, we also need to know what's happening to the substrate. And that's, unless it's a radical, usually invisible to the bioinorganic techniques. And so this method allows us to figure out where in a sequence of events we are by looking at what's happened to the substrate. A lot of times we don't get lucky and we don't see states, and so we have evolved strategies to alter the substrates, and use of heavy isotopes. We're interested in CH cleavage, so deuterium in particular can slow down those steps very well. But we can also chemically alter the substrate. We can alter the enzyme by site-directed mutagenesis. And we can change conditions, temperature, viscosity, things of that nature, to try to unmask these kinetically masked intermediate states. And then there are computational methods. And these methods are useful when we have some sort of gross spectroscopic data to figure out what structure gives rise to those data. And of course, Frank and his ORCA package are hugely important in this field to figure out what a Mossbauer spectrum what structure is giving rise to that Mossbauer spectrum, or EPR spectrum, or MCD, or any of those things, right? And so the computational methods are exceedingly important here. And to interpolate between the experimentally detected states, when you have this collapse and you're missing 3 or 4 states, DFT and other methods can tell you what are reasonable structures to get from the couple of things you see through the things that you can't see, right? But I am extremely skeptical about conclusions derived this way. And I'll give you one little example why. But I think done well, you really can't get to the level of insight that we want without using DFT methods. And I think guys like Ed Solomon and Frank are extraordinarily successful in this. So they're most often right, but I still evaluate their conclusions very carefully. And ultimately, I want an experiment to test it. So I view the value of these computational interpolations as primarily being to inform the design of a new experiment to test the idea. Okay? The conclusion by itself is interesting, but it's a hypothesis to be tested. Okay. So, I want to mention and give particular emphasis to this goal, which is to understand how enzymes suppress other pathways that are invariably possible when we're doing this potent chemistry that I'm going to focus on. Okay? And one thing that you can't escape, you absolutely have to remember, is that in our experience, in no case has a detailed dissection of the mechanism of the enzymes we're interested in that are activating oxygen and cleaving CH bonds failed to reveal the existence of multiple pathways. Not sure what that is. Okay. So what these things can be, we almost always, I would say always, have heterogeneous reactants. Anybody know? Okay. So we can have two different reactant states that might converge on the same intermediate with different rates. We could have a reactant state that interconverts between unreactive and reactive forms, where the enzyme in this form has to take on the reactive form before it can progress through the reaction sequence. And the thing that we've encountered very often is that we have some unreactive form that we don't understand that simply doesn't interconvert. It never goes on. It's just dead, and we don't know why. And this really is a huge challenge, because when you would ordinarily want to use information from amplitudes, from amounts of things, to make conclusions about kinetics and mechanism, you have to always remember that you could at any given time be looking at a population of your molecules, of your enzyme, that's heterogeneous, where one state is doing nothing and the other state is doing everything. Okay? So for example, if I have an enzyme and I measure the rate, the catalytic rate of that preparation of enzyme, and I get that it's 1 per second, in the absence of any other information, I could have 1% of that sample doing all of catalysis at 100 per second, or I could have 100% actually working at 1 per second. And in the absence of other information, I just don't know. So it's really hard in some cases in metalloenzymology with complex oxygen-sensitive cofactors that can fall apart to know what is the active state. And that becomes a central challenge that we've gotten, I think, pretty good at here at Penn State. The other thing that happens invariably in our chemistry is that intermediates can go by two pathways. One in particular, these iron 4 intermediates can often, they pull off hydrogen atoms, including methyl groups, so really difficult chemistry, and they'll lead to formation of products, but sometimes they fail. And especially when we challenge them with a heavy isotope of hydrogen, with deuterium, they'll fail a lot, right? And so we always have to keep in mind that we're going to see kinetics of bifurcating pathways. And there's some really interesting outcomes that come that are not always intuitive to people about the kinetics of branched pathways. Okay, so the techniques that we use here, you've seen these now. Hopefully everyone either has done these before and knows them, or decided to avail themselves of the practical sessions. Stop flow absorption, in its simplest form, you just put two reactant solutions into two different syringes, and by either a pneumatic drive or a stepper motor, you drive those together. They mix and go into a flow cell, and you have a spectrometer that's shining light through that cell, and a detector. In our case, we have a photodiode array, by which you can acquire absorption spectra every millisecond. Okay? So you can get down into that millisecond regime. The second method is freeze-quench. Here we're firing two things together. Instead of observing them in real time, we're going to stop the reaction at a given reaction time by spraying it into a cold cryosolvent, or thanks to Jarrett Wilcoxon from Dave Britt's group, we're showing you how to use these new rotating metal discs to spray reaction solutions onto those to get them cooled rapidly. And in principle, that method allows for even faster cooling so that we can get freezing times in the millisecond and sub-millisecond regime and do reactions down into that regime. And then the last method is the chemical quench flow method. I abbreviate it CQF. Here we're just mixing things together and shooting them into acid-base organic solvent, and then analyzing what we get out, knowing that it might not be what was in there when we killed the enzyme, and we analyze invariably here by mass spectrometry. Okay, so those are the techniques. It's the approach, the techniques. Now let's just look at some examples and see how intuition can emerge and real insight can come about. So I'm going to focus a lot, and depending on how much time I have, maybe exclusively, on the enzyme taurine alpha-ketoglutarate dioxygenase, or tau-D. This is the first enzyme that Karsten and I worked on together after he arrived here at Penn State. Prior to that, we worked together when he was a postdoc with Vincent Huynh at Emory on these carboxylate-bridged diiron proteins, oxidases and oxygenases. And when he came to Penn State, Karsten's idea was, well, if we can do dinuclear enzymes, there's no reason we can't do these mononuclear enzymes. And they were really growing in importance as new members of the family were discovered. And we talked about it, and I had been following Bob Hausinger's work on this tau D enzyme, so we decided to work on this. And obviously it went well, and that sort of cemented the partnership. So what the enzyme does specifically is to hydroxylate C1 of taurine using this alpha-ketoglutarate co-substrate that's converted to succinate and CO2 at a mononuclear iron center that has 2 histidines and 1 carboxylate, and then coordinates the co-substrate in this chelating mode. We've seen this chemistry before in Dennis's talk, so I won't say more about it. But this reaction is a general, or is a specific case of a general chemistry by which aliphatic carbons can be hydroxylated, and there are hundreds and thousands of these enzymes, some of which are really important in human physiology. So we got in on the ground floor of a really burgeoning area. Because one of the enzymes is a prolo-4-hydroxylase that helps make collagen, component of human connective tissue, stronger by cross-linking it. And because a deficiency in that enzyme causes the disease scurvy, which is a vitamin C deficiency, and leads to connective tissue weakness, gum bleeding, and death if you don't get vitamin C. People have been interested in that enzyme since the 70s, and this group, led by Hanaska, Abel, and Gunzler, had proposed in the Journal of Theoretical Biology this mechanism. So basically what happens is the iron coordinates, there are 3 sites open that the enzyme leaves open to coordinate alpha-ketoglutarate. When the substrate binds, that last water is displaced to make this square pyramidal complex. This was originally shown by the methodology that Frank was just talking about, by Ed Solomon's group on clavuminate synthase. But it seems to be a general phenomenon. That loss of that last water upon substrate binding opens a site for oxygen to add, and it makes a ferric superoxide complex that's not been seen in any member of this family. And that then closes, presumably this intermediate's been proposed. Computational studies suggest that it's not really an intermediate, and that there's a distinct intermediate where CO2 has been lost, and we have this succinic acid coordinated. I think that's an interesting idea, but so far untested. And then at some point, there's decarboxylation, cleavage of the OO bond, and we get this iron 4 intermediate that pulls hydrogen off the substrate to make this substrate radical. And then there's a combination of the substrate radical with the coordinated OH ligand, which is acting as a hydroxyl radical. So they speak of this as a rebound step, although I think Dennis's sort of reinvestigation of this process, this step by which the radical and the ligand combine, is very interesting and provocative, and I think this is by no means an understood process, this radical recombination. So this was proposed in 1982, and there was no evidence prior to when Karsten arrived here in 2002. And so I had a student, J.C. Price, who started with me and then ended up being co-advised by Karsten. And he had a student, Lee Hoffert, who started with him and then ended up being co-advised by me. And they kind of rectified this situation for 2 enzymes, tau D and a prolo-4-hydroxylase from a viral species, JC on tau D and Lee on the P4H. And what JC did initially was to provide the first direct evidence for this ferrule intermediate, which had been proposed going back into the 70s based on analogy to heme chemistry. Okay? So that was published in a series of papers in the mid-2000s. And what he did then beyond that was to identify the accumulating states, and he could make this in a test tube just by mixing the enzyme with the two substrates, alpha-ketoglutarate and taurine, here represented as RH. And then he could mix that with oxygen, and what he found was, in addition to this ferryle state that accumulates, there's a product state with succinate and the hydroxytaurine bound. And so here, our 8-state mechanism collapses into really 3, as this thing is turning over at maximal velocity in the test tube, 3 accumulating states, okay? And
Are you stopping the reaction at each of those points?
no. The experiments, as you'll see just in a minute, we start with this complex. We call this the quaternary complex because it's the enzyme plus iron that we had to add, plus alpha-ketoglutarate plus taurine. And that you can stop, because if it doesn't have oxygen, it doesn't go anywhere. And then we mix with oxygen, and it flies through and comes back to here in most experiments. If we have limiting alpha-ketoglutarate, it'll have to stop here. If we have limiting oxygen, it'll come all the way back to here. If we have limiting taurine, it would stop here, right? So we could have it stop anywhere we want, but in principle, the important thing is we're looking at a single turnover, because that makes analysis simpler according to chemical kinetics, not steady-state enzyme kinetics, right? Okay, so the experiment in its basic form illustrates another general principle. The most versatile way to study chemical dynamics, although it's inherently limited in time scale, is by mixing of reactants, right? So these are mixing methods, but you want the thing to initiate fast, right? You want to have a state that is very reactive and gets into the cycle quickly. So what you need is to mix the enzyme with all the substrates that add first, and add the one that is supposed to add last in the mix that initiates the reaction, right? So in our case, oxygen always adds last, except in the AURF experiment that you guys did in the stop flow practicals. That's one rare exception. And so we know that in this field, we're going to mix together the enzyme and all the substrates and put that in one syringe and then shoot against oxygen as the last reactant. There are very few exceptions to this rule, but the general principle is you want to mix with the last substrate to start your reaction, because then it'll go fast, right? And so in the tau D case, we knew that we had a chromophore from this ternary complex without taurine, and we can see that by titrating iron in and watching this feature at 520 nanometers, 530 nanometers grow in. That's from a metal to ligand charge transfer transition, with this carbonyl ligand being the key, providing sort of the acceptor orbital there. And you can see we can count the number of iron sites. We could see binding of taurine. Bob Hausinger had shown this before, as a very, very subtle shift in the lambda max of that peak. And so we had a handle on the reactant complex. Okay? So we knew we'd see something go away if a state with if intermediate states accumulated. So we did the mix, and this is what the raw data looked like, and I think it's a little better than Dennis's case, but not much. It's not too impressive. What we knew when we left out oxygen was nothing happened. So these subtle changes we could believe, and what we did, as Dennis showed in his talk, was to just present different spectra, because they look a lot more spectacular. And here's a blow-up of those. And so we saw some subtle changes. And the first thing, when you see data like this, you want to count states, okay? So the goal here is to determine the minimum number of states necessary to count for spectra, then to deduce time dependence of the states that you can count, so you know where to freeze when we're going to do these freeze-quenching experiments. And then we want some minimal kinetic mechanism that relates the species that we can see accumulating. And the tools in doing this are, first, visual inspection. If you get good at this, you can tell I have at least X number of states just by looking at these spectra. Ultimately, mathematically, you can do this rigorously by global analysis, singular value decomposition. I'm not going to show that in a previous lecture. Alexei Silikov talked about that in the 2014 workshop. Nonlinear least squares fitting, like I did on Karsten's email, according to some model, will tell you sometimes when the model is insufficiently complex to account for the data, meaning there has to be another state, right? But one really has to understand these models. And randomly fitting data can lead to spectacular mistakes, incorrect conclusions. And then because fitting usually requires a model from which you need to be able to exactly solve the differential equations to get an analytical solution, and that's not usually the case when you're mixing reactants at comparable concentrations because you have second-order kinetics. Simulation methods, in particular a program we use is called Kintex Sim, designed by Ken Johnson and his company, allows us to escape the shackles of having to have an analytical solution. You can plug in a mechanism, concentration, and rate constants, and it will numerically calculate the concentration of every species in that reaction as a function of time. So this is extraordinarily important in our analysis. So by visual inspection, if you look at these data, what you see is initially at an early time, 20 milliseconds, there's a peak here at 320 nanometers. It's a little bit uncertain where the real maximum is because we're getting into where the protein cuts off there. And we see at that same time we've lost some of the intensity. There's a negative feature here, but it's shifted. It's at 600 nanometers, not 520. And so this is one state that has a absorption at more than the reactant complex at 320 nanometers and less at 600 nanometers, but it compensates at the near the maximum of the reactant complex. And so it's isospestic there early on, right? Then a little later, 200 milliseconds, we see that peak is now negative, and it's sort of where the lambda max of the reactant complex is. So this looks like a transparent second state. So we have the reactant state, we have a UV-absorbing intermediate state, then we have a transparent intermediate state, and at long time, because we had limiting oxygen, excess alpha-ketoglutarate, and taurine, we reform the exact same state, and we get a flat line in a different spectrum. So there's three states, right? And you can contrast that with a reaction. Here's the AURF that we used in our practical, and I'm just looking at the binding of an inhibitor, this para-hydroxybenzoic acid. And when you look at that, you see that this phenolate to iron charge transfer band grows in as the thing binds, and the mu-oxo to iron charge transfer band is lost. And notably, there's an isospestic point in there, right? So this is only two states, right? So that's the difference between seeing 3 and seeing 2. And you can count those by eye, but you can also see them in the kinetic traces. So really understanding just by visual inspection requires looking at spectra, trying to see how many things you need, then going to the kinetic traces. And when you look at the kinetic traces here, you plot the wavelengths where something interesting is happening, and you plot 320 nanometers, and you plot 520 nanometers. And what you can see is there's a maximum here at about 20 milliseconds and a minimum here at about 200 milliseconds. Those are clearly interesting points to move on and do the stop time experiments and the freeze quench and the chemical quench, okay? And so that's what we did. We did freeze quench Mossbauer, which we had sort of developed in my PhD work at Emory. Vincent Quinn and Dale Edmondson and I had sort of designed the cells and the methodology to quench into a Mossbauer cell, and you guys are seeing that here in the workshop. And so what happened was, at an early time, we saw this new quadrupole doublet feature, and Karsten's talked about this. And at somewhat later time, it's hard to tell, but there was a really slight shift in this high-energy line corresponding to the ferrous reactant complex, and that's the transparent second state. So in the Mossbauer spectra, by choosing good times to quench, 20 and 200 milliseconds, we could see these two states independently. And this one was by far the most interesting, this new quadrupole doublet. It had an isomer shift of about 0.3 millimeters per second. Karsten's talked about this. And from the intensity of this doublet in Mossbauer, the beauty of the proportionality of the signal to the concentration, according to the assumption of a constant recoil-free fraction, allows us to get the concentration of the species. And optical methods won't do that unless you know the molar absorptivity, which you never do when you're discovering something new, right? So that's, and here, what I point out is that we started with 1.3 millimolar reactant, limiting reactant, and we only got 70% accumulation, less than that, but the kinetics suppress it somewhat. And so what we knew right away was only 70% of our enzymes active, and this was one of the first cases where we saw this heterogeneity. We still don't know why 30% doesn't want to do anything, but we see it in every case we look at. Okay, so you got to keep that in mind. So this is heterogeneity where some fraction of the reactant state is not really reactive. Okay, so it was interesting historically, the isomer shift of 0.3 millimeters per second, although isomer shift usually can tell you something about oxidation state. That one sat right in the middle of ferric, high-spin ferric with that coordination with those ligands, and what we would expect for iron 4, although there wasn't really a good precedent for that. And so an experiment that we did where Karsten took the initiative to find out that we had this Brazil nuclear reactor facility here. I didn't know about it. And we could do this gamma radiolytic cryoreduction, was to take a sample enriched in this iron 4 intermediate and reduce it. And if it's ferric, we should get ferrous back. And if it's iron 4, we should get ferric back. And what we saw as a function of radiation dose is a decrease in this resolved peak of the ferro complex and formation of these new magnetic features from an S=5 halves high-spin ferric ion. So we knew that this thing was iron 4 from this really neat cryoreduction experiment. And we could see the ferric product of that radiolytic reduction grow in better by EPR, right? It was easier to see. So as I told you, the way my mind works, we had this new thing. We didn't know what it is. I didn't ask, how does it look? I asked, what does it do? And that's what J.C. Price did with me. And he synthesized the deuterium-labeled version of taurine, knowing that if this is that mythical iron 4 intermediate that's been proposed now for 30 years and never seen, that if you put deuterium there, the iron 4 is going to have a harder time pulling that off because of the kinetic isotope effect that is usually attributed to a lower zero-point energy for the carbon-deuterium bond, but it's actually has much more to do with tunneling probability. And so when JC looked at the kinetics by stop flow with the protium substrate, that was the trace. With the deuterium substrate, that was the trace. And if you look at the separation here, this is a log scale, that's about a factor of 37. Okay? So that looks like a huge kinetic isotope effect. And we did what I believe may be still the first accurate measurement of an intrinsic KIE by Mossbauer spectroscopy by doing the same freeze-quench Mossbauer experiments in a kinetic sense, and we could see that same 37-fold separation. So what that told us is if you believe the mechanism of Hnask, Abel, and Gunzler, and what people have been proposing for 30 years, is we had in our hands this iron 4 oxo intermediate. But it really didn't say how does it look, and that's what Dennis did by his incredible, beautiful continuous flow resonance Raman experiments that he's already told you about to show that it had the iron 4 oxo stretching frequency that you'd expect and establish that it's a ferrule. A few months later, we finished the study with Pam Riggs-Galasco using XAS spectroscopy to establish the presence of the short metal ligand scattering interaction that you would anticipate for a ferrule, for the ferrule unit. So that showed that it was ferrule, and we had these 3 states, and it became JC's job to map those onto the chemical mechanism. So this is like the minimal kinetic mechanism. That's what it collapses to in terms of what accumulates. And he had to map that on to what we believed increasingly was a reasonable mechanism proposed many years earlier. And so that became the rest of his PhD, and what he was able to show were these rate constants, some of which we measured. Oxygen adds at 1.5 per molar per second to this reactant complex, and then we go quickly through here to the ferrule. So the first accumulating state is this iron 4 oxo. There's then a hydrogen abstraction, which has a rate constant of 13 per second with protium and 0.3 per second with deuterium, and that forms a radical, presumably, but that state doesn't stick around, and that goes right to the product state. And then the slow step in this enzyme reaction, and this is more often than not true, is product release. So all the interesting chemistry happens, and then the product release is slow. Okay. So how did he do that? Well, we interrogated the substrate binding steps sort of qualitatively. What he showed was if he mixes the tau D iron complex without oxygen with alpha-ketoglutarate, which also lacks oxygen, there's really rapid formation of this chromophore at 530 nanometers, so that it's mostly missed in the dead time of the stop flow at high concentration. And interestingly, he could show that this order of binding that people had proposed was true by, if he pre-incubated with taurine in the stop flow experiment, it actually slowed down formation of the chromophore, because with taurine bound, alpha-ketoglutarate can't bind. So if taurine is pre-bound, it has to pre-dissociate before alpha-ketoglutarate can bind. And this experiment is when he mixed them together, it goes in fast. So the enzyme knows how to bind alpha-ketoglutarate first, and then taurine when it's presented with the two simultaneously. So it was clearly that alpha-ketoglutarate binds before taurine. He then took the quaternary complex, formed that ahead of time, and put that in syringe A, and mixed that with varying concentrations of oxygen. And what you can see is that the formation kinetics are approximately first order in oxygen. This goes from low oxygen concentration to high. These are simulation lines from that program kinetics sim. So it's imperfect agreement. What could that tell us? Why might it deviate? Well, one possibility is that we have a preceding intermediate, right? And we struggled with that and did some additional simulations. And the truth is we can't say that there's not something accumulating. But what we know, and what I tried to tell you guys when I gave the practicals, is that this early times are often plagued by mixing artifacts. So we think that the deviation there is from mixing artifacts. Then I asked what would happen if there was some non-covalent complex with oxygen prior to that first intermediate. And a lot of enzymologists are conditioned to expect that. We expect to see a lag then in formation in the change in absorption, because you had to form a complex first and then it reacted. And we simply don't see that. In fact, we have no case where there's any evidence for a non-covalent enzyme-oxygen complex, despite the fact that that appears in the literature all over the place. Okay, so then that kind of shows that we go rapidly to the ferro complex. The other question was, if we believe that this is a ferro, this co-substrate should have been decarboxylated. So this is where the chemical quench flow experiment comes in. Can we look at alpha-ketoglutarate? So we bought C14 labeled alpha-ketoglutarate, and we could do the chemical quench flow experiment, and with the same kinetics that the iron 4 intermediate forms, we see C14CO2 accumulate. And so that established that when that intermediate state is formed, one of the substrates, alpha-ketoglutarate, has already been transformed to succinate. Then JC asked, can we show that in the transition of this intermediate state to the transparent second state, is taurine hydroxylated? And so here is, actually this was Eric Barr's experiment, single turnover chemical quench flow using protium taurine and deuterium taurine. You can see that with the same kinetics that this iron 4 decays by Mossbauer and stop flow, we see formation of, this is actually detecting sulfate, that's a breakdown product of taurine, hydroxytaurine, with the same kinetics and with the same isotope effect. Now note, there's actually a separation here between these two traces. So the amplitude of the D-taurine trace is lower. And this again reflects what I told you, this inevitability of branch pathways in this chemistry. So what happens is the wild type enzyme, the enzyme with the normal substrate, protium substrate, is able to efficiently process taurine to hydroxytaurine. But challenged with deuterium, there's a significant failure exposed. So I'll just step through to the actual explanation. So here's tau D transforming protium taurine, and it is able to pull this hydrogen off, leading to hydroxylation at 13 per second. And what we didn't know, because we couldn't see it, is there's a second pathway that leads to decay of the intermediate without hydrogen abstraction. And so that's a failure process. The rate constant's a meager 0.1 per second. So you wouldn't even know that's happening if you look at just the protium substrate, right? 13 compared to 0.1, that's no competition at all. It looks completely coupled, right? But as soon as you put deuterium there and slow the intrinsic hydrogen deuterium abstraction rate constant down to 0.3 per second, now that 0.1 per second competes. And now you see 25% failure, 75% success. And that explains why the amplitudes of these traces are different by 25%. Okay? Now, we used one of our rare steady-state kinetic experiments to show that the rate-determining step is product release. This is looking at the steady-state activity as a function of solvent viscosity. And what you can see is with protium substrate, when product release is rate limiting, this slows down with increasing solvent viscosity because it's a physical step. But when you use the deuterium taurine, it doesn't slow down as much because now the rate limiting step is the hydrogen abstraction, right? And so that proved the nature of the rate determining step. And then finally, product release, the order of product release, which is hydroxytaurine first, followed by succinate, was revealed by the kinetics of reformation of that reactant complex as a function of taurine concentration. So at high taurine, we saw this really slow reformation of the reactant complex at the end of a single turnover with oxygen limiting. Why is that? Well, after hydroxylation, we have this product complex. Hydroxytaurine has to come off first and then succinate. But once hydroxytaurine comes off, there's an open binding site for taurine. And if taurine concentration is high, it binds and traps succinate on the enzyme. Because when taurine's bound, succinate can't dissociate, right? And so if you blow up that sequence, what we saw in that slow phase is a trapping, an unproductive trapping of this product complex, which prevents loss of succinate and reformation of the reactant complex. And so that was the kinetic dissection of taurine alpha-ketoglutarate dioxygenase. And what the rest of my presentation shows, I'm not going to go through it, but you can look at it online, is how we used that framework then to deduce the basis for selective chlorination of an aliphatic carbon by these chlorinases that Chris Walsh discovered in 2005, where a similar intermediate abstracts hydrogen, but instead of transferring the hydroxyl group, the chlorine group transfers. And this all came out of kinetics. The computational chemists, there were 4 studies prior where they got it wrong, and structural methods would definitely not have revealed the basis for that. So that's in there. And then the last thing in the presentation is a dissection of the mechanism of this enzyme, carbapenem synthase, which is involved in synthesizing carbapenem antibiotics, one of the still useful beta-lactam antibiotic compounds. And so by this combination of stop flow absorption, freeze quench spectroscopic methods, and chemical quench flow, we can go in and see what's going on in a reaction sequence and understand the structural basis for guiding, for how the enzyme guides that process and ensures that other pathways don't occur. So I think I'll stop there and let everybody have lunch. Any questions?
Yeah,
I have 2 questions. One is, how do the kinetics you measure relate, and can you produce a correlation with overall kinetics, like turnover rates measured in solution assays, for instance? And the second question is something that I might have misunderstood, is when you say that you block the reaction pathway
Right.
in one specific state by limiting the one of the reactants, how do you take into account the fact that the affinity of the reagents for each other can produce heterogeneity in the sample?
Right. Yeah, that's a good question. So enzymes that bind more than one substrate often have a sort of synergy or cooperativity, if you will, where binding of one impacts binding of the other. But if there's an order, it's valid to study binding of the first one in the absence of the second. It's not really valid to study binding of the second in the absence of the first, right, if there's a kinetically preferred pathway. And so that needs to be deduced, but once you know that, you can then study the reaction in segments up to a point. Once you give the enzyme everything it needs to do chemistry, it goes. And that's when you're at the mercy of nature and kinetics as to what you can see. The other question is a very good one. I think you were asking, if I can get there, you were asking about the relationship between the kinetics that we measure and what you would measure as, you know, an old school enzymologist in the steady state, right? Is that what you wanted to know?
Exactly.
Okay. Yeah, that's a great question. So in kinetics, it's funny that the faster a step is, the less it matters, right? So there's this concept of rate determining step. And I think it's a useful concept, but people get confused by it. If you look at this sequence, this rate constant greater than 3 times 10 to the 4th per molar per second. This says fast because we couldn't measure it at all. And now oxygen adds at 1.5 times 10 to the 5th per molar per second. These are all second-order processes, meaning bimolecular reactions. And what kcat is in enzymology parlance is it's the rate constant for the cycle when all second-order steps become so fast that they no longer matter. And that's by high concentration. So kcat then doesn't care about this, or this, doesn't care about that. All that matters are the two steps that are unimolecular and can't be affected by concentration. And so we have the hydrogen abstraction rate constant of 13 per second, and we have the product release rate constant of 2.5 per second, right? So which is the rate determining step? The slowest one. However, this one is also partly rate limiting. So if you want to know, if you end up with two rate constants that you're worried about, you want to know how fast will the cycle that depends on those two go, all you have to do, this is the method of net rate constants by the late, great Mo Cleland, is take the product of these two rate constants, 13 times 2.5, over their sum. When you do a product over a sum, it's going to turn out that the smaller one dominates. So if you take 13 times 2.5 over 13 plus 2.5, you'll get 2. So the predicted kcat for this cycle is 2 per second, right? The measured kcat is 1.4 per second. Can you tell me why? It's not bad, but it's significantly different. Anybody know the answer? Maybe somebody from my group can say. Remember back when we did the Mossbauer experiment and only 70% of the enzyme reacted? In a steady state experiment, you dump in a certain amount of enzyme and you measure the concentration by UV. You can't distinguish the active guy from the inactive guy. In the transient state experiment, you can tell because not enough accumulated, some of it didn't react, right? So it's heterogeneous. So only 70% is reactive. So the transient state experiment is measuring the approach to completion. It's really the amplitude is not in that number, right? So when you compare a steady state measurement to a transient state measurement, you have to know what fraction is actually doing catalysis. And so if you get the predicted value of 2 and you multiply by 0.7, you get exactly the measured value that we got when you looked at in the steady state. It's a really important point of how you relate classical steady state kinetics to transient state.
Is the active fraction at millimolar concentration necessarily the same as at the steady state concentration, though? So, I mean, that's a cute figure, but that could be just an artifact, right?
Because we don't know what the explanation for the 30% inactive fraction is, You're absolutely right. I mean, it could be that because the Mossbauer experiment, you start off with 2 millimolar protein. Actually, no, it was way more than that. It was a 2-to-1 mix, so it's 3 times the concentration of something like 1.4. It's very high. It's like 5 millimolar. You could get aggregation, and the 30% you don't see react could be from aggregation. Or it could be there's some unknown post-translational modification. The way Jeff told us, when you do mass spectrometry, every protein he gets, there's something surprising about it. There could be some modification. For example, in tau D, it's known that there's a tyrosine that can get hydroxylated. Hausinger and Larry Kay and others showed that. So there could be some modification. So as long as the explanation for why that 30% fraction is inactive holds at both concentrations, the argument works. It's possible that it wouldn't, but we've gotten, in cases where we've gotten accurate enough measurements to know, more often we've seen that active fraction seems to apply both at the low, steady state enzyme concentration and at the under the transient state conditions. But it's a valid point.
Well, given that the time is already up, maybe the rest of the discussion should be under saturating beer in the evening.